All right, testing 1, 2, 3. Yeah, those levels look okay. So hey, I'm gonna do this whole video a second time because I blew it the first time. The first time through it took me 32 minutes. So maybe it'll be about that same amount of time this time, but hey, how's everybody doing? Hope you're well. I want to do a combo video here. First part, I'm going to walk you through DeltaMath and how it works. Second part is I'm going to do the DeltaMath activity that is a review for the quiz. So that'll give you your content as well. I would recommend as we go that if you want to do the problems, just click pause and then do them. Then click unpause and see if we agree, right? See if we have the same answer. See if my explanation jibes with your explanation, maybe more to the point. You can check if you're right or wrong by just doing the DeltaMath, it'll tell you. But see if your explanation, see if your thought process is aligned with mine. If that matters. Anyhow, let's get into it. To access DeltaMath, you obviously can just type DeltaMath into Google. That might be your best bet. I have it bookmarked right here. Type DeltaMath. And then once you're there, you bookmark it or do whatever you want to do to normally access it. You're going to click login and log in with Google. It's probably your best bet. So when I log in, I can see every single lesson that's available. They're kind of color coded, like pre-algebra, algebra, geometry, etc. Going all the way up to reasonably high level, I guess just BC. A couple of things. They're calling this CS, computer science, I guess. Yeah, sure, whatever. So if you cats are on your way to multivariable, they don't have anything for that yet. But anyway, if I go to Tools, Sample Student page, this is going to be what you guys see. And I've been doing this wrong, obviously. I apologize. You guys have been coming here and it's just been nothing. For those of you that have been coming here, I think I thought I was sharing the assignments and I'm sure I was doing it wrong, so oh well, I apologize. I'll make sure that you guys are getting these assignments from now on because they're pretty good. Here where it's asking me for a due date, I'm just making something up. I just said September 30th to give you guys 10 days to do it if you want to. It's not a real assignment. Oh, it remembers me? Oh no. So maybe it's going to act like I already did this. I wish it wouldn't do that. I don't know if I know how to do that though. Whatever. Maybe it doesn't matter. I'm just going to keep going. But you guys don't have to do this. It's not like mandatory. It's just optional. I think I'm always going to use DeltaMath as supplemental practice problems, never for an actual assignment. But as soon as I say never, one of these days I'm going to be really busy. I'm going to need a sub-plan or something like that, and then I might push this out and say, hey, this one counts, okay? But in general, I think that they're not going to count. Anyway, once you're here, just click on it. Click onto this first activity. It's saying we want to find limits graphically. Now the reason why I wish this didn't remember me is because it's asking me to do 5 problems, right? And I think there's a lot of problems available. I think it randomly pulls a set of 5. So you and your buddy might get 2 different sets of 5. And hopefully that means as I go through, maybe I'll be seeing new problems too. But look in here. It's pretty great. Like it says here, use the graph of the function f of x shown below in order to determine the limit as x approaches 6 from the right of f of x. So you find 6. Limit from the right seems to be 3, but I'm like, oh geez, it's a whole, so maybe it's not 3. If I want to say does not exist, notice you don't want to type that. There's a special key here for does not exist. If you want to answer with infinity, it's giving you those options too. It says obviously there's not a way to type infinity on your keyboard really other than using like alt codes or ASCII codes or something. But it'll give you these special characters even if you don't need them. They're obviously not going to put it up only when it's right, or else you'll just pick it. But we don't want it. But let's say we did want it. Type. It puts it there for you. Okay. Let's say you have no idea what's going on. This program has built-in videos. I did not know that, but now I do. So let's take 10 seconds to watch a video inside of a video.
Side. Therefore, the limit as x approaches a of f of x does not exist. Now, suppose we were to slightly modify this.
Yeah.
And
yeah, there you go.
X graph
Long
below and
pause.
x is equal to.
Anyway, so there's videos here. So this is awesome. I mean, I'll keep making my videos as much as I can, but this is something we might start to lean pretty heavily on, especially if these videos are really, really good. I'll let you guys watch them and report to me whether they're great or not so great. But we can hide that video again. We can do the problems. We already said, since we want the limit from the right, it's just going to be the 3. You just go here, type 3, say submit. It'll prompt you, hey, are you sure? And you'll say yes. And you'll see what used to be a black question mark turns into a green check. It's also doing a kind of cool thing. We talked about how to evaluate these limits numerically. And so notice they're starting just to the right of 6, and you can see the ball moving slowly left, and they're showing you data. And so as we go from 6.9 to 8.765, we're getting closer to 6. You can see these numbers getting closer and closer to 3. Now it's saying exactly 3. I'm sure it shouldn't be exactly 3. What happens sometimes is if you're getting 2.9 to 9 to 9 to 9 to 9 to 9 to 9, it's going to round that off and say it's 3. But we wouldn't really get exactly 3, because what's our x value that it stops on? Yeah, if our x value is out to the 10,000th place, we wouldn't be at exactly 3. That's a round off thing. But we still would extrapolate from the behavior that the number that we're approaching is 3. So we did it. Proud of us. Moving on. I can go to next section because when I was recording before, I already did my 5. I believe Ms. Lee set this up to where you have to get 5 right before you can get to the next section. If you get a question wrong, it drops you down by 1. So then you have to like fight back, I guess. So if you get 1 right, 1 wrong, 1 right, 1 wrong, I think you might get kind of stuck in this endless cycle. But oops, oh well. Next question, bonk. So is this different? It's asking for the limit as we approach 0 from the left. Yeah, I didn't see this question before. So I think there really is a very large pool of problems here, which is great for you guys that just want to like drill and drill and drill. If there's people out there that really like to just do a bunch of practice to really nail it down, this would be the place for you, because you don't even have to stop at 5. You can keep going to next question instead of going to next section. You can ramp this thing up to I got 13 right out of 5 requested if you want to. That's not me. I don't like to do a bunch of practice. I like to learn the concept broadly and whatever. Everyone's different. So what's the answer this time? The limit from the left would be 1. So you enter 1. Bonk. I assume you guys could expound upon this and talk for days about how there's a removable discontinuity here, and it's because the left-hand limit is 1 and the right-hand limit is also 1. But the function value is something else. They're not asking about any of that. They just want to know the limit. So just say 1, submit, yes, done. And then move on. I don't think I'll do more of these because these are pretty simple. I think you guys get it. I'll do one more. Why not? But they're just asking you for a limit, either from one direction, or I think there were some bi-directional questions in here. But at -4 from the left, you can see we're going to approach this value of 3. These are simply not that challenging, so let's move on. Okay, so I'm going to go to the next section. Bonk. What is the next section? Can I just kind of open this up again? When they say section, the sections are defined by the sections that we assign to you. Page. So we just went from finding limits graphically. We're now going to do vertical and horizontal asymptotes as limits. Then the next section is types of. The next section is continuity. So I suppose if you got sort of trapped, like I was saying, getting one right, getting one wrong, right, wrong, and you never could like get to the 5, but you really wanted to move on, it seems to me you could back all the way out and then just click into the next part. You could jump to continuity. The finding K is the part I really want to get to. We could jump to that. You guys have the freedom to move around as you want to, since it's all optional anyway. But I'm going to keep just going. The way this runs, I think it's self-explanatory, and I think it's really well designed as well. Wish I thought of it. But it says there are a total of 0 vertical or horizontal asymptotes. Well, I see 2 verticals, and I believe they're trying to have these end behaviors here. I believe they're trying to treat them as asymptotes as well. So there's a total of 1, 2, 3, 4. So when I set this to 1, it prompts me to tell them about the one asymptote that I think I see. If I set this to 4, it prompts me to talk about all of them. And I'd like to think I can do these in any order. I'm sure it's programmed intelligently. So let's do this vertical one at 5. Let's do that first. Then it prompts me to say, hey, why? Why is there a vertical asymptote there? And it's just a drop down. I assume you guys would pick the right one, but we can see that the limit as we approach 5 is negative infinity. Make sure you pick the one that has us approaching the right x value and with the limit of the right y value. It's that one. Let's now do the horizontal one that's way the heck over here at -2. That is an end behavior asymptote, so it's going to be governed by the behavior of the function as the x's go left to negative infinity. So find the one that has us heading towards negative infinity with a limit of -2. Choose that. We've got that one justified. Now we'll go to the vertical asymptote at 2. It's at x equals 2. As soon as you plug in 2, now it's asking you why. Why is it that? And again, it's a vertical asymptote. Ooh, what have I done? Okay, so this is at -2. I almost screwed that up. So we're going to approach -2, and the limit is negative infinity. So we've got that covered. There's another horizontal asymptote that occurs at y equals 3. And that is because as x goes to positive infinity, the x's go to 3. So there's 4 asymptotes in this function, and I've defined them all. Submit answer. Yes, I'm sure. Green check mark. Okay, I'm killing it. Notice that finally, now that we've submitted, it does give the dotted lines for those asymptotes. I stand by what I said, that if I was giving you a graph, I would draw those asymptotes. Maybe not the vertical ones. Those are pretty obvious. But for the horizontal ones, we talked about how you just don't know really whether this graph is behaving asymptotically or whether it's just, moving really, really slowly. If this thing here was a log function, then you guys should know that log functions, they grow and grow and grow without bound. They do not have a horizontal asymptote. But if this was a branch of a hyperbola, then it would likely have a horizontal asymptote and a vertical asymptote. We don't know that unless they give us more information about the equation of the function f of x. So I will typically either give you the function rule so that you can see it's a log function, so there would not be a horizontal asymptote, or so that you can see it's a rational function, so there is. Or I'll just draw the things in. Drawing them in is probably what I'll have to do. Anyway, the explanation here isn't much. It just says the answer, but there are some problems where it explains a little bit. But I'm going to keep moving. Next. This is the same. What do we got? It looks like 2 horizontals and a vertical. I'm not going to do this unless it forces me to. I think I can leave, right? Next section. We're now into types of discontinuities. Good. So we're into a new type. Watch the help video. I assume it'll be different since it's talking about a different thing.
Well, if I write down the limit
Yeah.
as x
So she's about to
approaches
classify this as a jump
-6 from the
discontinuity. So as you jump to the different sections, there's different videos. You could watch them. How long is this? It's only 5 minutes, right? It's just 5 minutes. You got a cog, so you can change the speed. I really prefer to listen to people talking fast, so I might set it to 2.
left of f of x does not equal the limit as x approaches -6.
These people in these videos, they talk really slow, right? You can crank them up to 2, and typically it sounds just fine. Maybe that's true of me too. Maybe you should crank me up to 2. Probably it is. Anyway, the videos are great. I think the activities are pretty great. I've been really impressed so far. So anyhow, reading this, it says the graph of the function is shown below. State all the values of x in the open interval from here to here. for which the function has a jump discontinuity. All right, it says open interval, but the endpoints are actually dots. That's fine. That just means the domain would be a closed interval of x values. But they're saying don't give me -9 or 9. So if you thought there was a discontinuity at -9, you wouldn't give it because it's not part of the requested window, the requested interval. Moot point, because they're not discontinuities there anyway. So we're looking for the jump discontinuities. I'd like to think you are keying in and seeing it right here and only here. So the answer is 7. Boing. Submit. Yes. Notice they didn't ask you to justify it, but also notice once you submit, they justify it for you. It says a jump discontinuity occurs when the limit from the left is not equal to the limit from the right, and there's not a vertical asymptote. Because if there was a vertical asymptote, then the discontinuity would be an infinite discontinuity. So, again, this is a well-designed question. You find the jump discontinuity, you give your answer numerically, and they do give you a bit more of that background info so that you can use the right vocabulary and stuff if you find yourself having to justify it to me. Next. They're asking now for the removables. For a removable discontinuity, we need the left and right hand limits to be the same. These limits are clearly different, so that's a jump. Here the limits are the same. So that's a removable at -1. Then you keep looking because it says state all the values. There could be more than one, but there isn't. Not this time. So submit. Yes. Super proud. Moving on. This time they want removables. Okay, great. There's a removable at -4. And then, there is another one now. This is what I've been waiting for, by the way. I wanted you to see that if you want to enter more than one, as soon as I hit comma, watch what happens. Boom. It splits and gives me a second answer field. It also opens a set of braces because we're now giving our answer as a set of values. We're saying the x's at which we have removable discontinuities belong to the set that contains -4 and also 0. This is also just a good way to signal that you're not giving the point, -4, 0. You're giving two different x values, right? You're saying -4 and 0 are the two locations. So they put in braces. If you wanted to open another field, you just hit comma again. It just happens automatically. And if you didn't mean to, I couldn't find a way to make it go away, like backspace, delete, clicking back over here. Nothing will make it go away, but it doesn't matter. You just leave it blank, and when you hit submit, it's showing you this is your set. It's -4 and 0 only. Say yes, we're right, everything's fine. So you guys see there could be multiple responses, and there's a way to enter them. So that's great. I think I'll go ahead and skip out of this because I think you guys have been really good at graphically identifying your types of discontinuities. So next section. Continuity, they're just asking us, are we continuous, yes or no? And this bears some explanation, so I can explain as we go. But we said to be continuous. The definition of continuous had three things. Had three bullet points is what I said. I've never done what I'm doing before. I'm going to do it right now. Whiteboard. Oh, I had to install it. Okay, this was a bad idea. Alright, I'm not doing that anymore. What I will do instead is we'll go here and I'll pull the thing. And then I can talk about this. Yeah. So what are those three characteristics of a function that is continuous? We said that three things have to happen. First thing that has to happen is f of, now we're trying to be continuous at -3, but in general, if you're trying to be continuous at c, then f of c has to be defined. And saying that it's defined, it just means that when you plug this value in, you actually get a real value out. You don't get an imaginary answer. You're not undefined. You don't get division by 0. You get just a regular old answer out. So is that happening here? If I was going to evaluate f of -3, well, to which interval does the -3 actually belong? This one, right? Because it has the equal to bar underneath it. So the value of the function comes from the top expression, So it would be 9 minus 4 times negative 3 squared. That's 9 minus 4. I don't know how fine I have to break this down, but that's 9. So that's 9 minus 36. So that's negative 27. So that's a real value. So the function value is defined, and it happens to be 27. So for this problem, I'll say this thing is 27. Now you also need the limit to exist. So the limit as x approaches c for the function f of x exists. Notice it's the bidirectional limit I'm talking about. The left and right hand limit, they typically exist. But for the bidirectional limit to exist, remember, we need the left hand limit and the right hand limit to equal each other. So again, for this problem, our left hand limit is going to be given by the values of x that are less. So the bottom expression, so we'll go ahead and do the negative 20, technically minus 6. So that's negative 26. And our right hand limit would be given by the same expression that gave us our function value. We don't really have to do the math all over again. We know it's going to be the same thing, and it's going to be negative 27. And DeltaMath, I don't know, they think they're cute, giving us two y values that are really, really close together, but they're not the same. And that's our third bullet point, right? Is if this limit did exist, then we need the function value to be the same as the limit. So we are definitely discontinuous. You're going to click this button and you're going to click submit. You know, I mentioned in class that you are going to have to actually explain where we broke down. We didn't break down here. The function was defined, but we broke down here. The limit did not exist because the left-hand limit and the right-hand limit were different from one another, right? Now, this is how I explained it. It's how Ms. Butler explains it, probably how Ms. Lee explains it. DeltaMath does a little differently. They take this and they do just split it into the left and right hand limits having to be the same, which is smart because essentially now you can just say, here's what has to happen to be continuous. You need your left hand limit to be equal to your right hand limit, which has to be equal to the function value at c. It's basically just these are the three things you have to test. This thing alone is bullet 1. These two things together essentially are bullet 2, because as long as they're equal, then the limit exists. And then this equal sign here, that's your bullet 3, where you're saying that the two things equal each other. So that's a great way to think about it. So anyway, heading back, I think all I gotta do is click. Yeah, we said we're gonna be discontinuous. Submit. Yes, I'm sure. Scroll down. They're explaining it to you here. They're saying determine whether it is. Here's the statement. Now here they're saying will be continuous if these three things happen. Left-hand limit, right-hand limit, function value. They're explaining over here that's the definition of continuity. So now they're checking the left side limit, the left-sided limit. I call it the left-hand limit. Different people are going to say different things. But essentially, I like what they're doing here. Instead of just saying generically the limit of the function, they're actually grabbing the appropriate expression and putting that where the f of x would have been, because we can take the limit of just the expression, and of course you get it by just substituting in the negative 3 and evaluating. So here's the values. It says the left and right hand limits don't equal each other. We can say that we're discontinuous. It's there, it all is. Okay. Let's do another, because why not? So here you go. Are we continuous or discontinuous? Well, you're going to plug in 2 to get both the function value, because 2 belongs to this interval, and 2 plugging 2 in here will also give us our left hand limit, because it's the one where the x's are less than that, so they lie to the left. Left. My camera's reversed. I'm not going to do that right. No one's looking at me anyway, are you? Checking to see if my dog's here. You guys might look at him if he was here. Plug in 2, 4, times 2, 8, plus 7, 15. Okay, remember that number. Now plug it in. Oh, 15. So left hand limit equals right hand limit. And it does equal the function value. So we are continuous. Yes. And again, it'll explain. I'm right. Why am I right? Because left hand limit's 15. Right hand limit's 15. Function value is 15. And when all of those things are the same, we are continuous. Okay? I hope you guys are starting to see the value in this. It's pretty darn powerful to have these questions. These questions are pretty well aligned to what we were doing in class. They're well aligned to what's going to be on the quiz. And there's just a bazillion of them. You can do as many as you want until you're really, really comfortable and confident that you're doing them right. And I'm comfortable and confident, so I'm moving on to the next section. Bazinga. So now we get to the find K part. These I'm definitely going to go through with you. There's one in particular that I'm kind of waiting for to come up for sure. Notice this is the first one I got for find K back when I was still at 0 out of 3. It gave me this problem. And notice I'm getting a different one now. So this one, k squared plus 80x, blah, blah, blah. This one is completely different. We'll go ahead and do this one. That should be here. And these should get deleted. All right, so this one. So how do you find a value of k to make sure that our function is continuous? Well, we said in class, and I felt like you guys were getting it, that we need to make sure the left hand limit is equal to the right hand limit, which has to be equal to the function value. In this case, it's at 9. I'll just go ahead and say f of 9. So who's going to give us f of 9? This top expression will. And that's where x's are greater than 9, so that's literally also the right hand limit. So these two things, for sure, they're already the same. They both are just going to be what I get when I plug 9 into this expression. So 7 times, or negative 7, times 9 plus 24 is negative 63 plus 24. This is the kind of arithmetic I cannot do. 39? That feels right to me. I'm going to go ahead and trust myself. Okay, but we also need this to equal the left-hand limit. And the left-hand limit is going to be given by this expression. This expression involves a k. So when we go to plug the 9 in for x, we're going to have an equation. We're going to have 9k equals 3. Okay, silly me. 9k minus 3. And we need that to equal the same thing as our right-hand limit. So you set it equal to your negative 39. You got yourself an equation, so you solve it. I'm going to go ahead and add 3 to both sides. So 9k is now equal to, adding 3 gives me negative 36. Then I can divide by 9. And apparently if I let k be negative 4, then these functions will meet together at the same point. And we will be continuous. So again, the idea here is k is negative 4. So this expression is a line with a negative slope coming down, 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 da, da, dee, 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 dee. And it's open. And the other one is like here. And it has an even steeper negative slope. So the deal is that value of k, as our slope is going to make it so this graph, oh boy, I could animate this a lot better if I was in Desmos. For now I'll just say, let's just pretend that changing the value of k just slid us up and down. If we were in any other position, we would have a jump discontinuity, right? But for a certain value of k, we can engineer it so that our graph just meets up with the other one. And then there's no break. There's not a jump discontinuity anymore. They meet cleanly and we're continuous. That's what we're doing when we're trying to find the appropriate k value. I don't know why I'm saying if I had Desmos. I have Desmos. And I even have this exact situation, I think. This one? Yeah, perfect. Look, as I animate the c value, it's going to change the slope. And you guys can see that at some point, I can make it so that I have just the right slope that I can close up my little discontinuity. I guess I already showed you all this, so hopefully it made sense then. But it looks like I can't get there perfectly because I think the right value was negative 2/3. Oh my god. 2/3. Bonk. And you can see now that everything matches up nicely for that one specific value of c. But no other c value would have done it. That's our situation. How do I... Oh, I just have to take that away and it'll go back to being a slider. I need you to be a slider. Yeah. Okay, so anyway, you can see for any other value of c, we'd end up with a jump discontinuity. But for just the right c value, we can be continuous. Next. Wait, give me more. I want more. Oh, I have to answer this one. I don't want to. This one's stupid. Alright, fine. I kind of have to. Negative 63 and 24. Isn't that the exact same numbers from before? So 39. And then this is... Oh, I never answered it. You dummy. Oh, what a dummy I am. Alright, what was it? The answer was the negative 4. Let's just enter it. Negative 4. Submit. I'm right. I'm great. Next question. Not what I was looking for. This is kind of more of the same. They're tricking us into thinking like this is going to be a quadratic equation, but it isn't because we are plugging in for x. So x isn't even really our variable. X is our constant. Here's what I mean when I say that. We're not going to end up with an equation that has x squared in it anymore because we're plugging in for x. So when you plug in the 2, you just get 4. And this gives us 4k, which is a simple linear equation. And we need that to be equal to what we get when we substitute down here. So it's going to be what? 2k plus 4. This isn't hard. We subtract the 2k, we get 2k equals 4. We divide by 2, we get 2. So k is 2. Easy peasy. Shebang. Submit. Accept it. Great. Moving on. Aha! Would you look at that? This time, the squared is on the k. And I'm not plugging in for k. I'm plugging in for x. So by the time I plug in the negative 3, I will still have a quadratic term. So this guy's going to be quadratic. This is what I wanted to talk about. We spent all that class time going over the systems problem and stuff like that, but we never did get to one that was quadratic. So, shrink. Let's do it. So you plug in 3 to get your right hand limit since the x's are greater here, and you're going to still have k squared, like I said, because we're going to get a quadratic. 18 times 3 is going to be 54, so minus 54. We're going to plug negative 3 into this expression to get our left hand limit and our function value, so it'll be negative 3k. Now, okay, I said it was going to be quadratic. I didn't say it would be all that challenging. To solve this, you just want to get it into standard form. So you add 3k to both sides and get yourself set equal to 0. Now you have to solve by factoring. And who are the factors of 54? Negative 54 that will give 3. Well, if it's negative 54, then I want two factors whose difference is 3. That's feeling like a 9 and a 6 to me. Nailed it. I want a positive 9 and a negative 6. So, plus 9. And technically, you're going to give your answer as a solution set. So you'll say k is an element of the set that contains. And you put your answers in numerical order when you're entering entries into a set. So we'll go negative 9 first, then we'll go 6. But because we were solving for a quadratic variable, you have to expect there's going to be two answers. So both negative 9 and 6 would satisfy the situation and make us continuous. Let's go back and enter those and see that we're right. Negative 9, negative 9. Now hit comma, boom, it enters you into set notation. It gives you a new field in which to enter your 6. So I gotta believe if I just wrote the word and, no, it's gonna get upset about that. If I wrote the word or, it just won't even let me. It's not a or. It should be an and anyway. It shouldn't be an or. But anyway, let's go 6. Let's leave this one blank. Let's submit. Yes, nailed it. All right, so there you go. That's everything. I went through all of these things. This is a good representation of what's on your quiz. We talked about continuity. We talked about limits. I really think many of you are going to find tomorrow's quiz to be not that bad. And it is 9:15, so let me hurry up and try to get this thing posted for you guys. So I'm going to just shut my mouth and move on. Have a great night. I'll see you guys tomorrow.